Hello, let's continue with the last two topics in this lecture 3. And this is the control system performance and stability. So first we discuss what is the control system quality. Includes some definitions on the factors. So that's system disturbances. So that's basically we will talk about. There is different type of disturbance, and as we talked about before, this transient is basically a random signal get into the system, and this transient, because the random signal, it's hard to model that signal, and also it's hard to describe the system response. But the set point change and the load changes, as we talked before, these two signals we can model as a step signal. So step signal to model these two changes, and this is most often the disturbances for a control system we will try to analyze. And there's a optimum control. The optimum control, the definition of optimum, that's basically say this system is not perfect or even very good, but it means that it is the best the control system can achieve. And this optimum control measured by three factors: stability, minimum deviation, and minimum duration. So the first is the stability, a very important concept for a control system. So that basically is say we want to provide a stable regulation of dynamic variables, and this stable regulation means simply means is we don't want the dynamic variable does not grow without a limit. So we want the system reaction response finally goes to stable values without the this is to say sometimes it can go like oscillations without a limit, that the system does not consider as stable. Minimum deviation, that's we talked about before, is the overshoot. So basically the maximum deviation from the stable value, that's our sometimes we talk about in the oscillations there's an overshoot, and we want that overshoot to be small as possible. So we want the minimum deviation from the set value or the stable value from its set point value. Minimum duration is the disturbance caused dynamic variable deviation, and this time period we want it to keep as a minimum, as less time period as possible. And the system stability analyze, there is a source of instability. So that basically we will talk about what is the causing the instability is so the feedback path. Before we talk about there's a feedback path, and remember we have a summer in front of the control system. So basically the system input goes to the summer, and feedback goes back to the summer as well. So the difference, so basically we will subtract these two and get our error. System error is how we, by definition before we talk about from set point minus the actual measured value is our error. And we don't want this error, so this is saying at any frequency, this error will causing oscillation to start and grow over time. That can be instability in the oscillation. It's my I say this error can grow. So we want to limit this one. is stable for some frequency. A signal like random noise will eventually set system into oscillation. As the system transfer function, we could analyze, if we know the system transfer function, we could analyze system stability over the whole frequency range. And the tool we do the analyze is the body plots. Body plot is often used for system stability analysis. So you can see here we connect the previous, we want to draw the body plots using the MATLAB and or use the hand drawing, and it will be a tool for system stability analysis. And also once we do the tuning, this is system tuning, this is one method we can use body plots to do the tuning. Stability criteria, there is 2 rules for the criteria. Rule 1, and a system is stable if the phase lag is more positive than negative 180 degrees at the frequency for which the gain is unity. So gain is unity basically is 1. So we say the gain is 1, then we want the phase lag is more positive than, so that's basically less than negative 180 degrees. A system is stable if the gain is less than 1 at a frequency for which the phase lagging is negative 180 degrees. So this one is say if we cannot change this phase lag is negative 180 degrees, then we want the gain is less than 1. So this is only the basic requirement for optimum system. So basically, we don't want the subtractor to be end up with adding 2 signals. Once we add 2 signals, so you can see with the feedback continues to grow, the oscillation, the signal where it goes larger, the system won't be stable. So this is basically explain these 2 rules. So in general, a good stable control system usually has, so you can see this one is basically under these 2 rules, we want the gain is actually 0.4 to 0.5. So that's these 2 are the product of the forward pass times the feedback pass is 0.4 to 0.5. So we want less than 1. And then the phase angle is between these 2 values. Remember here is negative 180 degrees, but actually we want it has this range of value. So these 2 values will produce a slightly underdamped control system, which gives with the sample step input about 20 to 30% overshoot with a subsidence ratio of about 3 to 1. Subsidence ratio is defined the following. So there's so basically measurement, there's some concepts are used. So basically the peak resonance and the bandwidth, that's basically peak resonance is also the maximum offset, or the peak offset, the oscillation, the maximum value in the system. And this bandwidth is defined as a frequency band between which the magnitude does not fall below negative 3 decibel. And some definitions, that's subsidence ratio or overshoot. That's quite often we use overshoot and subsidence ratio. I think next lecture we will have a figure for this one. Settling time is the time taken for the response to fall within and remain with some specific percentage of the steady state value, such as 2% of steady state value as acceptable range. So once how long it takes, it will goes into this range. And this one use a zero pole plot. So that's basically this one only talk about here is about the poles effect on the system stability. It basically say if our poles is in the negative part, remember either we get a negative value or a negative pair of conjunction of the poles, then it will, so you have eventually it will reduce the oscillation to zero and stable at some point. Same thing for this one, is also stable at some point. However, if the poles on the positive range, you can see the oscillation will grows. So also this one is also grows. That means unstable region. So this one, take a look. We didn't talk about the zeros effects, but if you are interested, you can search for PID controller tuning. This is the Understanding PID Control Part 6 Manual and Automatic Tuning Methods. It's used in MATLAB. So that's basically it. We're talking about the zeros effects on the system response. So that's it also not only introduces how you use the MATLAB to do the manual tuning, and also MATLAB also has an automatic tuning. It's also shown here. If you are interested, you can take a look. And let's continue with last topic. So section 3.4 process loop tuning. So because this video is limited to 15 minutes, so we just go through this session quickly. So that's basically for a PID controller, that's we have some proportional integral and derivative control, or we write into this expression. So we have three factors, Kp, Ti, and Td. So for the tuning. So first we talk about the control mode selection. That's basic rules. So when we select the proportional control, when we use the integral control, and when we use the derivative control, and this one basically is giving the summary. So most proportional control will be always in this control scheme, and then for the flow control, level control, that's mostly we have a liquid flow in, and because we talk about a liquid flow, basically it's very noisy, and it will change quickly. So derivative is hardly used for this type of control, but the integral control is generally used for flow control. That's basically we want to get some damping or filtering action for the loop. So that's the integral control. And the temperature control, because it's considerably lagging time, so we basically will add this derivative control, adding the quick actions. And this one, analytical control is usually integral is added. Sometimes a derivative also added. This is the pressure control, and the same thing for the analytical. This always has a proportional control. Usually have the integral combined, and sometimes combined with derivative control. And we have three control method, open loop transient response, Ziegler-Nichols method, and frequency response method. These three didn't talk too much, but this will be our questions corresponding to the assignment 5, and we will talk in another video. And that's all. That's all for this one.